Welcome, everyone. Today, we'll be diving into the critical aspects of implementing GenAI serving infrastructure. We'll explore the key concepts necessary for successful deployment and scaling, ensuring your AI initiatives are not just powerful, but also scalable, secure, and optimized for your business needs. We're here to help you power tomorrow's AI today. Let's consider the journey of AI models, from their initial development to their real-world application. This involves several key stages. First, we have the training phase, typically an offline batch processing task. Then comes inference, which is online real-time processing. Finally, we need dedicated infrastructure to support users and applications. Our goal is to make GenAI models available, reliable, fast, and scalable. When it comes to production, there are core needs that must be addressed. Scalability is crucial to handle fluctuating and growing request volumes. Reliability and availability are paramount, ensuring high uptime and graceful failure handling. Low latency is essential to minimize response times, and high throughput is needed to maximize the number of requests processed per second. Finally, cost efficiency is vital to optimize your infrastructure spend. Let's take a look at the key components of a typical system. A user request enters through an API gateway or load balancer. This request is then routed to the serving layer, which manages deployment and scaling using containers and orchestration. The model server, using frameworks like Triton or TF Serving, handles model loading and execution. This is all powered by hardware accelerators like GPUs or TPUs. Finally, a response is returned to the user. All of this is supported by robust monitoring and logging. Powering efficient inference requires careful consideration of both hardware and software. GenAI is compute-heavy, demanding GPUs or specialized AI accelerators. Serving frameworks are essential for managing execution on this hardware. Optimizations are also key. Batching groups requests to efficiently utilize hardware. Quantization reduces model size and precision, for example, using INT8. Model compilation optimizes software for specific hardware, such as TensorRT and OpenVINO. Managing capacity dynamically is crucial for maintaining performance and efficiency. We leverage containers using Docker for packaging our models. Orchestration, often with Kubernetes, automates deployment and scaling. Horizontal scaling allows us to automatically add or remove model replicas based on load. Self-healing provides built-in health checks and recovery mechanisms, ensuring resilience. Monitoring system performance is essential for maintaining uptime and visibility. We need to track key metrics like latency, throughput, resource utilization, and error rates. Setting up alerts, categorized as critical, warning, and informational, allows us to proactively address issues. Designing for redundancy, implementing health checks, and monitoring key metrics are all vital for ensuring uptime. When deciding on infrastructure, we need to consider the trade-offs between cloud and on-premise solutions. The cloud offers managed services and elastic scaling through providers like AWS, GCP, and Azure. On-premise solutions provide more control, data locality, and potentially higher stable utilization. Security considerations include API access and network protection. The choice depends on factors like scale, budget, expertise, and data needs. Let's put it all together. At the top of our pyramid are the user applications, the end users and systems consuming AI. Below that is the serving infrastructure, which focuses on scalability, reliability, performance, and cost. The technical foundation supports this with accelerated hardware, serving frameworks, and orchestration. Finally, operational success is achieved through monitoring and a well-defined deployment environment. Remember, serving bridges development and user applications.